In this video, we'll be talking about the trace of a square matrix and some of its properties. Let's begin by looking at the matrix 2, 5, 7 in row 1. In row 2 we have 3, 2, 4. And in row 3 we have 9, 7, 5. The trace of a matrix is the sum of the entries along the main diagonal. That is, the trace of A is equal to the entry for A in row 1, column 1, plus the entry for A in row 2, column 2, plus any successive entries along the main diagonal until we get to the last one, A for the nth row, nth column. The trace of our matrix here is A row 1, column 1, plus A row 2, column 2, plus A row 3, column 3. That is 2 plus 2 plus 5. So the trace of matrix A for this square matrix is equal to 9. The first property that we'll talk about for the trace of a matrix is that the trace represents a linear transformation from the space of square matrices to the real numbers. If we consider square matrices A and B, where A and B are of the same order, and we have some constant C as a scalar, then we can say the trace of A plus B is equal to the trace of A plus the trace of B. We can also say that the trace of scalar C times A is equal to C times the trace of A. A second property states for any square matrix that we'll call A, the trace of A is equal to the trace of the transpose of A, where the transpose is found by writing columns as rows. Let's go back to our original matrix that we used as our first example. So here's matrix A. The transpose of our matrix A can be found by writing each row as a column. So row 2, 5, 7, row 1, will become column 1. Row 2, 3, 2, 4, will become column 2. And row 3, 9, 7, 5, will become column 3. The transpose of A is the sum of the main diagonal, as we saw before. So transpose of A equals 2 plus 2 plus 5, which equals 9. And the trace of the transpose of A is also equal to 2 plus 2 plus 5. Another property tells us that if A and B are square matrices, we should just say if A and B are matrices, and their product AB is a square matrix, then the trace of A times B is equal to the trace of B times A. If we consider matrix A, and we call it 1, 2, 3, 4, then consider matrix B, which is 4, 3, 2, 1. The product, A times B, is equal to 8, 5, 20, 13. And the trace of AB is equal to 8 plus 13, which is equal to 21. If we multiply matrix B times matrix A, then we get 13, 20, 5, and 8. And the trace of BA is equal to 13 plus 8. Again, 21. Another property states that if B has an inverse, and is a square matrix, of the same order as some matrix A, then the trace of A is equal to the trace of B inverse AB. Again, let's call matrix A 1, 2, 3, 4, and we'll call matrix B 4, 3, 2, 1. The trace of A will be found with matrix A, and then we'll set that equal to the inverse of matrix B, B inverse, which is negative 1/2, 3/2, 1, and negative 2, times the product of B times A, which we found to be 13, 20, 5, and 8. So again, we're following this statement here. The trace of A is equal to the trace of B inverse times the product of A times B. And actually I used B times A right here, so let me fix that. So let's simplify this on the next screen. So again, here we have matrix A on the left, then the product of B inverse times AB, the product of A and B, which gives us 26, 17, negative 32, and negative 21. Taking the transpose of each, transpose of A equals 1 plus 4, which equals 5. Transpose of B inverse times BA equals 26 minus 21, which equals 5. So this concludes a brief description of what it means to be the trace of a matrix, along with a few properties that you may run across. I hope you found this example helpful, and we'll see you next time.